Okay, so last time we saw that given a representation, you can decompose it into these blocks. Yeah. If G is a group and V is a G representation, then you can always write V as V1 dxm, V2 dxm, Vm, where these VIs are Wi for Ri, where Wi are irreducible G representation. Yeah. So Vi is a sub-representation of V such that it is composed of irreducible representation Wi's. Yeah. So it is certain number of copies of Ri number of copies of Wi. Yeah. And we saw that we can realize VIs and we can pick out VIs via these maps. Yeah, so these maps are PIs. So you can see these PIs are defined just in terms of the representation rho V. Yeah, and so you would know every irreducible character given a group G. You can find out all its irreducible character in some way. Yeah, and then using that you can compute this PI. And then the image of this PI, so PI is the projection map and the image of the PI is VI. Yeah. So that is, so VI is basically a unique subspace. So this decomposition is sort of unique. Yeah. And so I told you we'll do one example of how to use it to get these VIs. So I thought maybe since we were discussing this example, let's just do this itself. Yeah. So this S3 example. So we saw S3 is generated by two. So S3 we know what it is, and it has three conjugacy classes: identity, transpositions, and three cycles. And we computed all its irreducible characters. So one is the trivial character, one is the sign character, which basically which is also one-dimensional, and the function and the character is basically the sign function on S3. And the third is the two-dimensional character, which we computed using those formulas. Yeah. So there are some relations from between characters, which we observed by studying the regular representation, right? And using those relations, we got that the value of chi2 should be 0 for transpositions and -1 for three cycles. And for identity, it has to be 2 because it's two-dimensional. Yeah. So we know the character table for S3. So now, and we saw this, we know how to, so trivial representation and sign representations are easy to write down. Yeah. So it's just one-dimensional vector space. We just tell what the action is. Yeah, S3 action. Now the two-dimensional representation for which the character is chi2, I just said what it is going to be without actually giving you that this is going to be, this is the proof, but maybe you can use this. Yeah, so S3 this method to get the representation corresponding to chi2. So S3 acts on C3 via this permutation. So we saw that this is the permutation permuting the coordinates, and we saw that the diagonal delta is a sub-representation and is a trivial sub-representation, because if all the coordinates of so if you consider the line where all the coordinates are same, that is x equals y equals z line, the diagonal, then on that S3 acts trivially. Yeah, so that's a trivial sub-representation, and then it will have a, so since C3 is a representation of S3, you can decompose it as trivial representation plus something else, and that something else is the subspace x plus y plus z equals 0, or z1 plus z2 plus z3. So the coordinates are z1, z2, z3. Yeah. So z1 plus z2 plus z3 equals 0. So that's so you can see that S3 preserves that as well. Yeah. So now let's try to use this formula, and then one can argue that it is so one can compute the character of that representation and show that that is same as chi2. Yeah. So that was the computation we did last time. Now let's use this. Excuse me. Use this formulas to get to decompose C3 as V1 plus V2 plus V3. So we know that so it decompose it as V0 plus. So now we are using. So unfortunately, I used chi0 as the character of the trivial guy, and chi1 is the sign character, and chi2 is the second. So we will decompose it as V0, V1, and V2. So we know that V0 should be one-dimensional, and we know what it should be. V2 should be 0, and V3 we know what it should be, yeah, as subspaces. So let's try to do it using this formula. So the formula says that you look at P0, and P0 we can compute explicitly. So N0 is 1 because we are looking at the trivial character. So the formula for P0 is 1 over 6. And then we look at sum of character of G, which is same as the representation of G, because you are in one-dimensional case. So you have to take sum of these. So it's 1 over 6 identity plus if you these are the elements, yeah, 1 2 2 3 3 1 1 2 3 3 2 1. Yeah. So if you consider 1 2 with respect to this basis, standard basis, then you are switching the coordinates 1 and 2. Yeah. So you get this particular matrix corresponding to the action of 1 2. Yeah. So row 1 2 is this matrix. So you'll get some matrices, right? Because you are going to get some elements of GL3. Yeah. GLC3 is same as GL3. Yeah. So you'll get this particular matrix. If you look at 2 3, then you're switching the second and the third basis vectors. So you get this and fixing the first one. So you get this matrix and so on. Yeah. So I've written the others in the next part. So maybe if you do 3 1, then you get this particular matrix. Yeah. So which is written under P1 with a negative sign that comes here. And then if you're switching 1 2 3, you know how to do it. Yeah. So 1 goes to 2, so you get something there and so on. Yes. So these are the matrices. But when you add them together, then the first one. So you want to know how many ones you will have in the diagonal. Yeah. On the first diagonal. That is same as saying how many elements of S3 fixes 1. So of course identity fixes 1, and then the only other permutation which fixes 1 is just 2 3. Yeah. So you'll get 2 here. Then to get 1 to th entry, you want to know which permutation sends 1 to 2. How many permutations sends 1 to 2? So of course the transposition 1 2 sends 1 to 2, and the other one is this 3 cycle 1 2 sends 1 to 2. Yeah. So that's how you get this number 2 and so on. Similarly, how many sends 1 to 3? So this transposition 3 1 is there, and then the 3 cycle 3 to 1 is there. Yeah. So this is how you get these entries. So you get 1 over 3 1 1 1. So this is I mean, this 1 over 3 factor is to make sure that it is a projection. Yeah. So you want that when you apply it to the image of. So what is the image of P0? It's precisely the column space of this. Yeah. So which is same as saying E1 must be same as E2 must be same as E3. Yeah? The subspace generated by E1, E2, E3. Yeah. E1 plus E2 plus E3. Sorry. if E1, E2, E3 as the standard basis of C3. So which is the diagonal. So does this computation make sense? That image of P0 is precisely the diagonal. Yeah, and
Yes.
P0 is this matrix. Yeah, so it's very explicit. So for small, I mean, even if the matrices are big, it's so 4-dimensional, 5-dimensional, still you can do it by hand. But of course, if it becomes too big, then you may have to use some other method or maybe some computer to write down the explicit matrices. But maybe sometimes you can read it off the way as trying to do. Yeah. But in general, but one can there is an algorithm. So if you want to, so for smaller dimensional representation, 3-dimensional, 4-dimensional, 2-dimensional, you can certainly use this and do it by hand. For higher dimensional, it may be a bit too unwieldy. Now let's try to compute P1. So P1 is again 1/6, and then you get identity, and so you have to multiply. So remember the formula says chi1 g bar rho v g. Yeah. So and chi1 is the sign function, right? So sign of identity is 1, sign of transposition is -1. If you do bar, then nothing changes. They're all real valued. So what you get is I minus for transposition. So since this is this corresponds to a transposition, you get a negative sign. So the next 3 terms are negative, and then the last 2 are for the 3 cycles. So you get it with positive signs. Yeah. And if you add them, you'll see that you'll get 0. Yeah. So you just check. So I just checked, and we got the 0 matrix. So that tells you that the image of P1 is 0, which is what we had guessed, that and there is no sub-representation corresponding to character chi1. Then finally, for P2, you can use the same formula. So now N2 is 2, yeah, and the order of G is still 6. So you get 2/6. And now the formula is 2 times, so chi2 bar of identity is 2. So you get 2 times I. I mean, 2 bar is also 2. Yeah, so 2 times I, and then transpositions are all 0. The chi2 of transposition is 0. So it simplifies our calculation. We can forget the first 3 terms here. And then for 3 cycles, we get -1. So you have to subtract minus this and minus this. Yeah. And so what you get is 1/3, 2, -1, -1, -1, 2, -1, 2, -1, -1, 2. Yeah. So of course, the column space is a 2. So you can see this is a rank 2 matrix. For instance, everything. I mean, it's at least rank 2 because there are 2 linear independently. So 2 columns are linearly independent. The first 2, and I guess so you add these 2 columns and take the negative, you get the third one. Yeah. So it's, or you can see that the image of P2 is contained in is exactly Z1 plus is the subspace Z1 plus Z2 plus Z3 equals 0. Yeah. So image of P2 is a representation with character chi2. Yeah, because it's exactly 2-dimensional. So if you apply this theorem, what it says is that image of P2 is W2 power some R. Yeah, but here R has to be 1 because image of P2 is 2-dimensional and W2 is also 2-dimensional. So the character is precisely right. Okay. So you don't even have to compute the character. Just by applying the theorem, you know that it has to be chi2. In general, it's going to be some multiple of chi2, some power of chi2. Some power or some multiple of chi2. Yeah, there is some meaning you add. Yeah. So if it is so so the image, the character of vi is ri times chi I. Yeah. But here ri happens to be 1 because of dimension reason. So this shows that so this tells this gives us that irreducible representation as well. The third irreducible representation of S3. Does this make sense, everyone? I hope this this example tells you that this is a useful tool, meaning you can actually do some computation using this method. Yeah, if you are given some representation. So that was the objective, to work out this example. So also note that though V1, V2, Vm, etc. are some invariants of V, which you can read it out using these projection map, there is no unique way of decomposing, say, V1 into R1 copies of W1. Yeah, so there are many choices depending upon, you know, so it's like choosing certain, I mean, if you are given a vector space, a 5-dimensional vector space, there is no unique way of writing it as the sum of 5 one-dimensional vector space. Yeah. So similarly, V1 is, we know it's W1 power is isomorphic to W1 power R1, but there is no unique way of decomposing it. Okay. But if you fix some choices, then you can decompose it. So there is some one result which is a computational result which is proved in SEER, yeah, which tells you one way to do the decomposition. So I'm not going through that result, but I'll highly recommend you read it, because it's a good computational tool. And these are the things which will help you if you want to do actual computations in future. Yeah, so I'll suggest you read it, but it's a computational tool, and yeah, so it's not that complicated, but maybe it won't be used in this class, because we'll do mostly some abstract things about representation. And explicit decomposition of VIs may not be needed. So I'll see if later on, if there is a place where it is being used, maybe I'll give a proof, but I'll present it in the class as well, or I'll maybe ask one of you to present it. But do read it. Yeah, it's a good tool, good method. Any questions or comments? Okay. So last time we also saw that G is abelian if and only if every irreducible representation of G is one-dimensional. Yeah. So this we realized by noting that you know, the number of irreducible representation is in bijection with number of conjugacy classes of G. Yeah. And for abelian group, that number is same as the order of G. So in fact, one can excuse me. So in fact, one can extend this a bit. So let me take a pause. I have a somewhat important pause, so let me pause this and we'll continue. Okay. Yeah. Okay, so sorry, sorry about that. So yeah, let's continue. So G is abelian. Yeah, so when G is a group and H is a subgroup of G. So we can show that if G contains an abelian group, then of a certain index, then again you can bound the characters in some sense. Yeah? Bound the dimension of the characters in some sense. So let me do that. But before that, let's discuss this this. So if you are given a representation and H is a subgroup, then of course V, you can also think of it as an H representation. Yeah, so maybe this should have been called the definition. So definition of, so this is like a restriction of a representation. Yeah. So H representation via this thing. So, rho G to GLV is the map. You just restrict rho to rho restricted to H. Yeah. So you're just letting H act, elements of H act, and not the whole of G. So V, you can view it as an H representation as well. Yeah. Right. So if I take a so if I take a, so if so if V is irreducible G representation, and H is a subgroup of G, then is V an irreducible H representation? What can you say? Yeah. So if V has no non-trivial G representation, would it be true? So this is a question. Yeah.
No, sir.
No, right? So what's an example?
So we can take the trivial subgroup.
Yeah. So if you take the trivial subgroup, then of course it's far from true. Yeah. So then the representation is trivial. You can just decompose it into line, or you can take so any abelian subgroup. Yeah. So let G be a group and H be a subgroup with H abelian, and let V be a irreducible representation. So then, of course, as an H representation, it will decompose into the sum of line, sum of one-dimensional representation. Yeah. So we will use so you can use that to prove this thing. Yeah. So if V is an irreducible G representation, then you can show that dimension V is at most G colon H. It can't be more than that. Okay. So let's see how. Yeah. But before that, is there something else? Yes. So this is one way. So given a G representation and H is a subgroup, you can consider it as an H representation. Later on, we will also see that if you are given an H representation, you can cook up a G representation out of it. Yeah. So G is a group, H is a subgroup, and if you are given a H representation, you can cook up a G representation such that the original representation is a sub-representation, and a equivariant map from V to H equivariant map from with some universal property also. Yeah, and that is called the induced representation. So I'm not sure whether we'll talk about it today, but next class we will certainly get there. So let's see why this is true. Okay. So I think there was something else which I wanted to say. So maybe I'll just write here first that you take identity as a subgroup of G, then V is take sum of one-dimensional representation of the subgroup E. Yeah. So you can take identity or any abelian subgroup. It's the same thing. Yeah. But one abelian subgroup is identity itself. So I mean, saying that it's a representation of E is like saying that it's a vector space. You don't get any more information. Yeah? There's no other additional structure. And any vector space, you can write it as the sum of one-dimensional subspaces. Now let's see this. Yeah. So proof. Let V be an irreducible G representation, and since H is abelian, we can write it as the sum of W1 or maybe yes. WM, where Wi's are H modules or H representations. Yeah, maybe I'll also keep using these terms so that you familiar with both of them. Yeah. So now, of course, you look at two elements. So let's take G1, G2, G1 and G2 in G. Yeah. So this W1 is a subspace of V. Yeah. And G1 gives you a linear map is an endomorphism of V. In fact, it's an invertible linear map. Yeah. So it will send W1 to something. Yeah. So G1, or maybe actually we can use the thing rho V G1 of W1 is going to be some subspace. Is going to be another subspace. So maybe I'll instead of writing this way, I'll write it as G1 W1. Yeah. So you'll get some subspace is a subspace of V. Yeah. Because G1 is not in. If G1 was in H, then we know that this is actually contained in W1. Yeah, because the W1 are H modules. Wi's are H modules. And similarly, you have G2 W2. G2 W1 is also contained in V. Yeah. But they may not be same. Yeah. In general, but sometimes they may be same. So if so, note that if G1 and G2 are in same left coset, yeah. So if G2 is, let's say, G1 times some H for some H in H, then G2 times W1 is same as G1 H W1, and we know that this is an action. So you can first act via H and then via G1. But W1 is a H module, so this is same as G1 W1. Yeah. So if you have two, if G1 and G2 are in the same left coset, then you get the same subspace. Yeah. So so this if so G1 W equals G2 W if G1 G2 are in same left coset. So you can get for each G, you can get these subspaces, but there are not too many of those subspaces. They are precisely so. So if you look at this collection, G W, G in G, then this has cardinality same as G colon H. Yeah, it has cardinality at most. So even if they are not in the same left coset, we can have equality. But if they are in the same left coset, then we certainly have equality. So we have at most G colon H number of these things. Yeah. And what about W1? Yeah. And what about so if you look at the subspace generated by these guys, GW, so GW1, yeah, so I don't know how to write, yeah, so maybe subspace generated by these guys. What can we say about this subspace? This is a subspace of V, yes, because everything is in V. So the subspace is actually invariant under the action of G, yeah, because if you operate by G, then the generating set is actually invariant, yeah. So this is a G invariant, G stable subspace. Not invariant, but meaning G the action of G on this subspace takes it to the whole subspace. It doesn't fix every element of the subspace, but it's G stable. Yeah. So the subspace is G stable. So that means the subspace is a sub-representation of V, and hence of G sub-representation of V. Yeah. But V is irreducible. Yeah. So what does that tell us? So since V is irreducible, this subspace has to be whole of V. Yeah. So well, this subspace is V. And what can be the dimension of this subspace? So remember, W1 is one dimensional. Yeah. So Wi's are irreducible. Sorry, we were taking irreducible H modules are one dimensional. So I forgot the important part here. Yeah, so since H is abelian, each of these Wi's are one dimensional. Yeah. So V is m dimensional and Wi's are all one dimensional. So in particular, W1 is one dimensional. So what is the possible dimension of this V? So there are G colon H one dimensional subspaces, and they together are trying to generate something. Yeah. So it can generate at most G colon H dimensional subspace. Yeah. So this implies dimension of V is less equals G colon H, since GW1 are one dimensional. So W1 is one dimensional, and hence GW1, the image of W1 under a linear map, is also one dimensional. Yeah. So this is what we wanted to show. Okay. So yeah, so there is some idea of induced representation already here in some sense. But anyway, we'll talk about it next time. Okay. Any questions? Okay. So this is about yeah. So there is also one thing I wanted to say. So if you are given a representation, G representation V, and H is a subgroup of G, then then V is an H representation via restriction. Now what is chi V as an H representation? So maybe chi V H. Let's say V is a H representation. So that's why the notation is important. Yeah. So chi rho H from H2. So what is this? And GLV. So if I want to know the character of this, what is this going to be?
A restriction of chi.
Yeah, so chi V restricted to H. Yeah, because we are just taking the trace. Yeah, of rho H. Yeah, and that and in the ambient guy we are just we are taking the trace of rho G. Yeah, so it's just you look at the character of V as a G representation and restrict it to H. So that is what the character of V as a H representation. So computing the character is also pretty straightforward. So this notion restriction is a very nice operation. It's I mean, in some sense, it's a trivial kind of operation. Yeah. So making computation is pretty straightforward. Okay. Next, I think we'll talk about products. Yeah. Products of okay. Yeah. So I don't know if these parts are needed for the remaining discussion for the product, but let me just keep it anyway. Okay. So let G1 and G2 be groups, and VI be a GI representation. Then we can cook up a representation of G1 cross G2 by taking the tensor product of V1 and V2. Yeah. So what is the how do you define the product? So this is also a definition. Yeah. So you can define the representation on V1 tensor V2 of G1 across G2 via this thing. Yeah, rho 1 G1 tensor rho 2 G2. So in terms of matrices, we know what this matrix is. Yeah, it's the tensor product of matrices we talked about. Yeah? Or in general, you know, V1 tensor V2 we know, and rho G1 is a linear map on from V1 to V1, and rho 2 G2 is a linear map from V2 to V2. Then you can take the so when you take the tensor product, you get a linear map from so you can tensor product the maps as well. Yeah. So I mean, on pure tensors, we know how it works. Yeah. So maybe I can say this. Yeah. So G1, G2 dot V1 tensor V2 is G1 V1 tensor G2 V2. Yeah, so on pure tensors, this is how it looks like. But remember, a general element is not a pure tensor; it's sums of these kind of guys. Yeah. So then you just have to put sums both sides. Yeah. So in general, you'll get V in V1 alphas and V2 alphas, where you sum over alphas and you just put that. Yeah? So linearity. So then if you and then so to define all this for general vectors, general tensor products, you'll have to use the universal property and so on, because giving a map from tensor product to anything is a complicated affair. You have to do a bilinear map. But here you can also argue using the fact that tensor product is a vector space with basis. So if V1 has basis E1 to En, and V2 has basis let's say F1 to Fm, then the V1 tensor V2 is a vector space with basis EI tensor Fj. Yeah. And then define the linear map on basis via this thing, and that gives you. So that is how we are thinking of this linear map. If you are writing in terms of matrices, also that is how we will write down the tensor product of matrices. So is this clear? The definition of representation of G1 cross G2 on V1 tensor V2. Yeah. So, so in fact, what is true is that if V1 and V2 are irreducible G1 and G2 representation, then the tensor product is also an irreducible G1 cross G2 representation. Okay, and conversely, every irreducible G1 cross G2 representation is in fact isomorphic to V1 tensor V2. Okay. So in some sense, studying representation of G1 cross G2 is like studying representation of G1 and studying representation of G2. So, and then combining the information. Yeah, so you can always, so if you have a group which you can write it as direct sum of direct product of certain groups, then studying representation theory becomes easier. You just have to study the representation of each of these factors. So, so let's see a proof of this proposition. So before that, let's try to compute the character, because that is how we'll prove it. Yeah. So what is the character of V1 tensor V2? So V1 tensor V2 is a representation of G1 cross G2. So we just evaluate it at G1 comma G2. So it is the trace of this this tensor product. Yeah. So you remember what is this tensor product? Yeah. So what is this tensor product of? Maybe I should have recalled what is the tensor product of matrices. Yeah. So maybe I'll recall it here. So if A is this matrix, Aij's. Yeah. So since I'm recalling it, let's just write it this way: A11, A1n, AN1, ANN, and B is similarly something B11, B1m, and BM1. So they may not be of the same order. BMM. Then A tensor B. So yeah, so it depends upon the choice of basis. So I hope. Yeah, so I think this is the notation we used. It's either this or the other way, but anyway, A1n. So it's, you can write it as this block matrices. Yeah. And so B, ANN. Yeah. So it's a NM times NM matrix. Yeah. The order of the matrix is the number of rows and the number of columns is little n times little n. So if you want to compute the trace of this tensor product, so the trace is just the sum of the diagonal entries. Yeah. So it is A11 times trace of B plus A22 times trace of B plus ANN times trace of B. So that is same as saying it is trace of the first matrix times the trace of the second matrix. Yeah. So you get that the character of V1 tensor V2 is just character of V1 evaluated at G1 times character of V2 evaluated at G2. Is this okay?
Yes, sir.
Yeah. So now let's prove this. So we want to say, the reason we are doing this is we have a characterization of irreducible representation. What is the characterization of irreducible representations? Among all representation, we look at the character and take its inner product with itself. Yeah, this operation. This so if you take any character, then this is going to be a positive integer. But if it is an irreducible so it is an irreducible representation if and only this integer is exactly 1. This positive integer is exactly 1. So let's just compute this pairing. So this pairing is by the formula of this pairing is 1 over size of G1 cross G2 times the character square of this guy. So this times bar of this, yeah, which is just square of the absolute value. And then you use the formula that this character of the tensor product is the character of the product of these guys. And then summing it over G1, G2 in G1 cross G2 is same as summing it for G1 in capital G1 and little g, G2 in little g2 in capital G2. And the size of G1 times cross G2 is same as size of G1 times size of G2. So now you can just split this sum as product of groups. Yeah, so maybe this you can write it as 1 over G1 sum chi v G1 square G1 in G1 times sorry 1 over G2 summation in G2 chi v G2. Yeah. Which is same as inner product of chi v1 with itself. So this is on G1 cross G2, yeah. So maybe I should put this is on G1 and this is on G2. Yeah. So the sums are over different indexing set. Okay. So now if V1 and V2 are irreducible, then both these numbers are 1. And that implies that this number is also 1, which implies that V1 tensor V2 is irreducible. Yeah. So that proves one direction, that if V1 and V2 are irreducible, then V1 tensor V2 is irreducible. Now we have to show that given any representation of G1 cross G2, it is of the form V1 tensor V2 for some irreducible representation. If it is once it is of the form V1 tensor V2 for some representation V1 and V2, then I mean this process is all reversible. Yeah, so it becomes then V1 and V2 must be irreducible. But so in fact, what we will show is that these are all the irreducible representations of G1 plus G2. Yeah, so there is no more irreducible so somehow we will show that there is no other representation which is irreducible. Yeah. So there are ways of doing it. So one way is to say that so one way is to so we know that if we look at these characters of V1 tensor V2, we should say that this is a basis of all class functions on G1 plus G2. Yeah, that's one way. Or the other way is we know one formula using the regular representation. We saw that if we look at the dimension of these representations, so these we certainly know are irreducible. So if we take the sum of squares of these representation, the degrees of these representation, and they add up to the order of G1 cross G2. That means this is odd, yeah, because sum of squares of all irreducible representations of G1 cross G2 should add up to G1 cross G2. And if just these add up, then that's it. That means there are no other irreducible G1 cross G2. So we'll try to do the second approach, yeah. The other approach also you can do, that's given in here, so or you can read there, but we'll do this. Yeah. So for converse, let V11 to V1M1 be all irreducible representations of G1, and V21 to V2M2 be all irreducible representations of G2. Yeah, and let their dimensions be Nij's. Yeah, so dimension of Vij, I between 1 and 2, and j between 1 and m1 and 1 and m2. For these vector spaces, the dimensions are Nij. Then by the result proved in class earlier, using the regular representation. Yeah, so I just mentioned this so that it's easier for you to recall regular representation. So we decompose the regular representation, and from there we got this formula. Yeah. We get that size of Gi is same as summation j equals 1 to mj ni j square. Yeah. So here I is 1 and 2 for I equals 1. Or 2. For both, you can have this. No? So now if you consider the size of G1 times G2 is size of G1 times G2, which is the product of these two guys. Yeah. And you just expand it. So what you get is summation J1. So J1 equals 1 to M1, J2 equals 1 to M2, N1 J1, N2 J2 whole square. Yeah. So there was square here and square here, so that's whole square. Yeah. But N1 J1 times N2 J2 is precisely the dimension of V1 J1 tensor V2 J2. Yeah. And these are all these are certainly irreducible. Yeah. And V1 J1 tensor V2 J2 are irreducible G1 cross G2 representation. By the previous part. Yeah. So their sum adds up to G1 cross size of G1 cross G2. So we conclude that these are all the irreducible representations of G1. So you can't get any more. Yeah. So that completes the proof of this thing. Okay. Any questions? So this completes sort of the discussion that every irreducible representation of G1 cross G2 is of the form V1 tensor V2 with V1 irreducible and V2 irreducible. Okay. So maybe this is a good place to stop. I could. In 1 minute, yeah, it will be difficult to even define it. Yeah, now induced representation. So next class we will see induced representation. So we saw the restriction representation. We saw the product representation. Next class we'll do the induced representation.